This video will give an overview of the oxidation simulation. The theory behind this is found in section 3.5 of the documentation file, and a more detailed user manual is also found in the documentation file. The basic premise of the model is shown on the figure on the left. A buffer zone, which is shown here, placed above the domain, and is initially populated with some number of walkers that's meant to represent atmospheric conditions. The walkers represent a certain number of oxygen molecules, and they're initially populated in the buffer zone. The walkers then undergo a Brownian motion random walk diffusion down to the surface. The surface collisions are detected through a linear interpolation method, which is described in section 3.5. And based on a sticking probability law, they simulate the reaction of the oxygen with the carbon surface. This causes the material to recess, and as the material recesses, the buffer zone recesses down with it. The video here on the right shows an example oxidation simulation for a two-phase material where the gray is the carbon fibers and the brown is a phenolic that has been added to the carbon fibers. As you can see, because the reactivity of the phenolic is higher, it oxidizes at a faster rate. In order to run an oxidation simulation, the domain must first be generated either through a microtomography import or an artificial domain generation. The tutorials for this are shown in previous videos. For the purposes of this video, we're going to use the sample of fiber form that comes with the distribution of PuMA. We're going to select a 300 by 300 by 800 sample, which is shown here in red, with a voxel length of 0.65 and a threshold value of 87. At this point, navigate to the Oxidation Simulation tab. All of these inputs can be defined manually. However, to expedite the process, we will import them all from an input file. We'll use the input file that comes with the distribution of PuMA. So for now, we'll go through each of the simulation inputs one by one. The temperature, pressure, diffusion coefficient, mass fraction O2, and molar mass of the gas are all defining the atmospheric conditions of the simulation. The diffusion coefficient is a function of the temperature and pressure. The delta R in meters is the random walk length, which is basically the length of each walk before a new random direction is assigned to the particle. Gamma is the sticking coefficient, which is left to be at 0.8, and it corrects for the non-Maxwellian nature of the random walks. The size of the buffer zone is kind of shown here, and it's the length in the z direction of the buffer zone above the domain. This value has to be at least twice the value of the random walk. The random walk length, by the way, is typically taken to be about the characteristic length scale of the simulation. So in this case, we chose the fiber radius, which is approximately 5 micrometers. The size of the buffer zone, which is in voxels, has to be at least twice this value. The size of the diffusion length, which is typically left at 0, is the distance from the top of the material to the bottom of the buffer zone. The moles of O2 per walker define how many oxygen molecules are stored in each walker. Typically, this value ranges between e to the minus 16 and e to the minus 18. The density of the carbon fibers is typically left at 1700, but to expedite the simulation, we're going to lower it to something much lower. This loses the time accuracy, but for the purposes of this tutorial, we want to be able to visualize it in real time. At this point, we have a couple additional options, which involve the phenolic matrix. The simulation has the option to be run on just the carbon fiber preform or to add a phenolic phase. If a phenolic phase is desired, there are two different ways to add the phenolic phase. The first is to add it as a matrix which is in all the voids. So we can give an example here. So you can see here the oxidation simulation. the buffer zone shown in blue, the particles shown in red, is initially just being conducted on the fiber form. Now, if we say all voids as matrix and start a new simulation and visualize it, the brown now shows the phenolic, which has taken up all of the voids of the material. If, on the other hand, we just use a matrix coding of a specified radius, in this case 2.6 micrometers, and start a new simulation, the matrix has been coated around the fibers. This tends to mimic the behavior seen in for example, AQ61. The reactivity ratio is the reactivity of the matrix as compared to the fiber. Typically, this value is left around 10. The density of the matrix can be specified or it can be left blank. If the density of the matrix is left blank, then it will assume that the mass fraction of the matrix is 0.35, and based on the respective volume fraction of the matrix phase to the fiber phase, it will calculate out what the correct value for the density is, which is then shown over here. At this point, once all the inputs have been defined, the new simulation button can be pressed as we did before, and the simulation can be visualized. For the case of a matrix coating, since it has to go and coat each of the individual fibers, it can take a couple minutes depending on the size of the sample and the speed of the machine. Next, we're going to go through the runtime outputs. Once a new simulation button has been clicked, the simulation will run for one time step after setup, and some of the outputs will be displayed here. This is done so that you can check the outputs, see if the simulation is running how you want it to before you run it for the full duration of time steps that desired. The first output is the time increment delta t, which is the time step for each random walk. The next is the fiber reactivity, which is in meters per second and is calculated as a function of temperature. And this is the intrinsic reactivity of the carbon fibers as compared to the effective reactivity of the overall phase. The diffusion coefficient is just repeated from the calculation here. The number of walkers is defined as the number of walkers that are in the entire domain. The number of walkers in the buffer zone are the number of walkers that were initially populated in the buffer zone to maintain the constant value boundary condition on the top of the surface. Now, this walkers in the buffer zone should stay constant throughout an entire simulation, but the overall number of walkers will change. The buffer concentration, which is in kilograms per meter cubed, shows the concentration of walkers that are in the buffer zone. The carbon molar volume is another way of expressing the density. The grayscale reduction carbon and grayscale reduction matrix show the grayscale attenuation rate of each phase. Typically, this value should be no more than 25, so we'll have to adjust the density of the fibers to compensate for that. What you want is to select a value for the moles of O2 per walker and the value of the density such that you get an appropriate grayscale attenuation rate, with 255 being a full attenuation. Now bear in mind, any time that the density of the fibers is changed from the actual intrinsic density of the fibers, which is typically about 1700 kilograms per meter cubed, the simulation loses its time accuracy. The matrix density, in this case, since it was left blank, is calculated based on a mass conservation that was explained in section 3.5. The Sherwood number and reactivity rate contrast have to do with the verification cases and should be ignored in any other case. The buffer zone minimum and maximum show the minimum and maximum position in Z of where the buffer zone is. The TLA number, which is described in detail in section 3.5 of the documentation, quantifies the relationship between the diffusion and the reaction. So if the TLA number is very high, it means that the reaction is very high as compared to the diffusion, which means that all the reactions will happen at the surface since the particles are not able to diffuse down into the material very deeply. On the other hand, a very low TLA number means that the diffusion is very high compared to the reactivity, and the particles are able to fully diffuse down into the material before reacting. In this case, we call this volume ablation, whereas for a high TLA number, we call this surface ablation. These two here are just for your reference when running simulations. They relate to the TLA number, and basically it's the sticking probability for each phase. For a low TLA number, the sticking probability is going to be very low. If you're setting up a simulation and you find that the sticking probability is incredibly low, something like below e to the minus 6, it means that the simulation will probably take too long to run, and you'll have to vary the initial inputs. So since in our case our grayscale reduction here is a little bit higher than we wanted it to be, we'll change this to say 5. The next aspect we're going to discuss is the output options. There are a number of different options to output data or images during the simulation. The first option here, which is checked, is to visualize the simulation in real time. This won't actually save anything, but it will create an image every specified number of time steps right here. The rotate option will make the image rotate as that's occurring. Now, if make movie is checked, it will create the visualization and it will also save that image to a file. These can then later be combined to create a movie, which the instructions on how to do that are described in the user manual. The save simulation data option outputs the porosity and surface area as a function of depth at each time step that is specified here, step between files. Save TIFF stack, same basic idea. It saves the oxidized TIFF stack. Save triangles saves the triangles at each time step interval. These can all be different. The intervals here don't have to be the same. Now, finally, once the simulation is set up, all the outputs are set as they want, you can actually continue the simulation for how long you want it. You have to specify the number of time steps that you want, the megastep increment. And now what that means is that as part of the parallelization, which again is described in better detail in section 3.5 of the documentation, the walkers are split up into walker groups, which are then assigned to processors. These processors all run independently for a certain number of time steps, which is defined as the megastep, before coming back together and doing calculations, making visualizations or saving data or checking to see if the buffer zone needs to be moved down. This megastep is usually somewhere between 100 and 1,000. Now, the number of threads specifies the number of threads that are being used. For this machine, we have 36 physical cores, so typically we use values between 30 and 35 as the number of threads used. If your machine has, say, 8 cores, it's recommended that you use 7 or 8. At this point, the simulation can be continued via the Continue Simulation button. Alternatively, you can press Fully Oxidized Material, which will repeat this Continue Simulation until the material has oxidized all the way down. So now we'll see in real time the simulation occurring, maybe a little bit slow, but you can see that the oxygen particles are diffusing down to the surface and the surface is beginning to recess. So while that's running, I'll explain the last two aspects of the oxidation simulation. The first is the smooth surface button, which is typically only used for visualization purposes, and it's not used very often. But basically, if your simulation was fairly rough and you wanted to smooth it out, you can specify a new density as a function of the old density and then run it for a certain number of time steps in order to attempt to smooth that out. Obviously, in this case, you also lose time accuracy, so this is really only done for visualization. The oxygen concentration button, what that does is it runs a certain number of time steps specified here, typically maybe 100 to 1,000, depending on the number of walkers that you have. And it calculates the position of each of these walkers over this number of time steps. For this period of time steps, the density of the material is put to infinity, so the particles still react with the material, but the material does not recess at all. What this does is it tries to output the steady state oxygen concentration as a function of depth. So once it runs for a certain number of time steps, it will then output the oxygen concentration average over those time steps. And that concludes the overview of how to run the oxidation simulation. A more detailed explanation can be found in the PuMA user manual.